Hello guys, welcome back to your physics class. We will continue by explaining section 1 in chapter 6. The last two topics remain self-induction and eddy current. In this lesson, we will focus on the self-induction and we will explain the self-induction. What is the self-induction? Self-induction, the creation of an induced current. The creation of what? An induced current in a circuit due to the variation of its own current. By the variation of the its own current of the circuit. This phenomenon is called the self-induction. The equation of self-induction, how can you determine the induced EMF in a self-induction? EMF is equal to negative L delta I over delta T. So the current is the current is induced and the electromotive force induced due to the variation of the current of its own circuit. How? Look, guys, look at this circuit. This is the equation of self-induction. What is this? This is the equation of self-induction. Induced EMF in self-induction. Assume that we have an AC source, okay? And there is a switch here and a coil of wire. We have a coil of wire. And a light bulb is connected with this circuit. We have a resistance or light bulb, okay? And this is a switch. Guys, if you close the switch, what happens to the current? The current increases, okay? So if you open the switch, what happens to the current? The current decreases. Or if you have a rheostat, okay? By this rheostat, we can control the amount of the current. By increasing rheostat, by increasing the resistance of the rheostat, what happens to the current? The current decreases. And by decreasing the resistance by the rheostat, the amount of the electric current increases. In the case of like if you switch on the light bulb, okay? Sorry, if you switch on, the amount of the current decreases. The amount of the current increases, okay? So this changing of the current from 0 to the maximum, okay? This current passes through this coil. When the current passes through this coil, in this coil, the magnetic field is induced magnetic field, okay? Guys, look, by closing the switch of the circuit, the amount of the current gets more, increases. The electric current increases from 0 to the maximum. When the current passes through this coil, it takes some time to glow the light bulb. The light bulb does not glow up suddenly or immediately. The light bulb, it glows slowly. It glows slowly because there will be an induced current that opposes the current of the source. By closing the close the switch, the amount of the current increases, okay? In the this is like close the switch, close the switch, okay? When the switch is closed, the change of the current increases of the source, okay? And this change of the current, it goes to what? To change the amount of this current, it goes to when the current passes through this coil, when the current passes through this coil, this current produces the magnetic field, okay? So this magnetic field is changes continuously. Why? Because the current is changed, okay? So the magnetic field in turn induces a current, okay? This is induced current. Now we have another current here. This type of the current is induced current. Now how many currents do we have? We have two currents. These two currents opposes, okay? So the amount, the induced current is according to Lenz's law, the induced current opposes the change in the change of the current in the circuit, the change of the current in the source. Okay, so this phenomenon is called the self-induction. What is the self-induction? In the self-induction, is creating induced current. Creating what? Induced current. By what? By the variation of the current in its own circuit. Okay, in the same circuit, we can change the magnitude of electric current. When the current changes, magnetic field also changes. When magnetic field changes, magnetic flux changes. When magnetic flux changes, the current and EMF induced in this coil. Now, how many currents do we have? We have two currents: the current of the source and the induced current. In the case of increasing the amount of the current, the two currents becomes in opposite direction. Okay, so we have to subtract them to determine the net current and the resultant current between these two currents. But in the case of when the switch is opened, or when the current is dropped or decreased, the induced current in the coil it becomes the same direction, and the net current and the resultant current increases. In the second case, when the current increases, okay, like for example, so here the switch is closed, okay. Guys, when the switch is closed, what happened to the current? Current increased, okay. Sorry, when the switch is open, not closed, sorry. When the switch is open, but in the previous figure, the switch is closed. But in this figure, when the switch is opened, okay, what happened to the current? Current drops, okay, or delta A decreases. Delta A decreases. It means that current is changed. When the current is changed, magnetic field also changes. Okay, when current increases, magnetic field increases in the solenoid. When the current decreases, magnetic field also decreases. By changing magnetic field, is current induced in this case. Okay, now this is the amount of the current of the source, and when the current decreases into this solenoid, what happened to the magnetic field? Magnetic field also decreases. When magnetic field decreases, the change of magnetic flux occurred and also decreases. Changing magnetic flux, it goes to what? Induced current. Now, do we have induced current here? Yes. Okay. In the case of dropping and decreasing the current of the circuit, the induced current of the coil, according to Lenz's law, has the same direction of the current of the source. So that is why the net current and the resultant current becomes more and becomes large. So there will be a spark on this on the circuit, okay, on the switch, because both the induced current and the current of the source, they have the same direction. Okay, they have the same direction. Induced current and the change current of the circuit, they have the same direction, but they are still opposes each other. Okay, opposes each other. When the switch is opened, what happened to the current? Current decreases. When current decreases, what happened to the magnetic field in the solenoid? Decreases. When the magnetic field decreases, magnetic flux changes. Okay, by changing magnetic field, current induced in this circuit. Okay, now how many currents do we have? Two current. The current of the source and the induced current. This induced current is called the self-induction. Okay, so this is the definition of self-induction: the creation of induced EMF and current. EMF and current. Okay, in a circuit due to variation what? Due to the variation of its own current, the current of the circuit. Okay, this is self-induction. And how can you determine the induced current and induced EMF in a self-induction? By the variation of the current is equal to negative L, and instead of N we have L. Changing what? By changing area, the creation of the induced EMF and induced current due to the variation of the current, not magnetic field, okay? And also to determine the amount of the current, EMF divided by resistance. Delta A is equal to A2 minus A1. Delta A is equal to what? Sorry, delta I. Delta I is equal to what? I2 minus I1. If delta I over delta T negative, in the case of decreasing of the current, delta I becomes negative, and in the case of increasing, delta I becomes positive. If the current is reversed, I final is equal to I initial but in opposite direction. The amount of the current, it goes to change magnetic field and flux, and it goes to induces electromotive force and the current. The resultant EMF is equal to the applied field minus induced field when delta I increased. When does E resultant is equal to applied EMF minus induced EMF? When delta I is positive. Okay, in the case when delta I is positive, resultant EMF is equal to applied EMF minus the source, EMF of the source. How can we get this equation? Guys, look, EMF is equal to negative L delta I over delta T. Now I'm going to prove this equation. Guys, the relation between current and magnetic field is directly proportional. Magnetic field with the magnetic plug is also directly proportional. Look, when the current passes through the solenoid, magnetic field is equal to what? Is equal to mu naught Ni over L. What is relation between B, magnetic field, and current? Directly proportional. More current induces more magnetic field. So the equation of flux is equal to what? AB cosine theta. What is the relation between flux and B? Flux is directly proportional to the magnetic field. Sorry. To what? To the magnetic field. Now, if delta I increases, what happened to the magnetic field? Increases. When magnetic field increases, what happened to the flux? Increases. So can we say delta I is directly proportional to the delta flux? Yes, of course. Why not? When the variation of the current gets more or increases, what happened to the flux? Flux also increases. Why flux increases by increasing current? Because magnetic field increases by increasing current. Okay. Delta I is equal to delta flux. Okay. And so we can divide both sides divided by time. Okay. It's gonna be delta I over delta T, directly proportional to change flux over T, and time is negative N delta I over delta T, directly proportional negative N flux over delta T. Okay, and negative N flux over T is equal to what? EMF, directly proportional to what? Negative N delta I over delta T. According math basic, if you convert directly proportional to the equal, so you have to add a constant here. Okay, look, if you convert the directly proportional to the equal, you have to add constant times negative N. What does remain? Delta I over delta T. Constant times N is equal to what? Is equal to L. Negative L delta I over delta T. So this is the proving of self-induction, the EMF in self-induction. This proof is not important because the questions in the Wizari exam, all questions are multiple questions. Okay, there will be no proving and solving question. Guys, look. Now, L is equal to what? Is equal to constant times N. N times constant is equal to what? Is equal to L. This is the equation of self-induction that created by the variation of the current. In a self-induction, guys, look at this figure. We have a coil of wire and galvanometer measuring current, a DC source. This is the current of the source, and switch and the rheostat. Okay, what is the job of the rheostat? The function of rheostat increasing and decreasing the amount of current. By changing the rheostat, the amount of the resistor in the wire in the circuit changes. When the resistance changes, the amount of the current and the magnetic field changes together. Okay, guys, we have a coil and magnetic core. This is magnetic core, mu. Okay, by inserting the magnetic core, what happened to the magnetic field in this coil, in the solenoid? B is equal to what? Mu Ni over L. What is the relation between magnetic field and permeability, magnetic core? With the magnetic core is directly proportional. So in how many ways we can increase the induced magnetic field in a solenoid? By increasing number of turn per unit length, or by inserting an iron rod into the solenoid, because the permeability of the iron rod is more than the permeability of the air and the vacuum. So that is why with the magnetic core, magnetic field is by increasing magnetic core, magnetic field also increases. By increasing the permeability of the solenoid, the amount of induced magnetic field increases. By inserting this magnetic core, by inserting the magnetic core into the coil, what happened to the magnetic field? Magnetic field increases. When magnetic field increases, guys, what happened to the induced current? Induced current also increases. Okay, so we move the rheostat until the ammeter points to 50 microampere. The ammeter now it's reading 50 microampere, very low current. For example, when the coil, what do you mean by coil? Magnetic core, mu. What do you mean by coil? Mu, magnetic core. Magnetic core has directly proportional to the magnetic field. When the magnetic core is connected, when the magnetic field is connected, what happened to the permeability? Increases. What happened to the field? Increases. Induced current increases. This induced current, this is the current opposite the source of the current. Okay, by increasing current according Lenz's law, this increasing of the current here is opposes what? The current of the source. Okay, so that is why the reading of the galvanometer drops. By connecting a coil magnetic core, what happened to the reading of the ammeter? Drops, decreases. The reading of the ammeter drops. Okay, by connecting coil, this is the current of the source. By connecting coil, what happened to the magnetic field? Magnetic field increases. When magnetic field increases, flux increases. When magnetic flux increases, the induced current also increases. Okay, according to Lenz's law, the induced current is opposes the change of what? The change of the magnetic field and the current of the source. Okay, these two currents opposes each other. Okay, opposes. So the reading of the ammeter of the galvanometer 50 microampere. If this current opposes with the 50 microampere in the case of connecting the coil, what happens to the reading of the galvanometer? The galvanometer reads drops. Okay, the amount of the current drops. Current drops. Electric current drops because the amount of the induced current increases by connecting the magnetic field. Okay, indicating the decreasing in the current. The resultant current decreases from 50 microampere to maybe 40, 30. Okay, so the most important thing here, you have to know, by connecting a coil into the by connecting a magnetic core into the coil, the magnetic field increases, magnetic flux increases, and the amount of the induced current increases according to Lenz's law. This increasing is opposite to the current of the source, so that is why the resultant current decreases and the reading of the galvanometer drops or decreases. When the coil is removed, guys, another case, when the coil is removed, when the coil or magnetic core is removed, when the coil is removed, what happened to the induced current when the coil is removed? Permeability decreases. This is the current of the source. Permeability decreases. When permeability decreases, what happened to the magnetic field? Magnetic field also decreases. Magnetic flux also decreases. When magnetic flux decreases, the amount of the induced current also decreases. This decreasing of induced current is opposite to the source, so that is why the resultant current becomes more. Okay, and this changing of the current, it goes to this decreasing of the current is opposite the source of the circuit, so that is why the reading of the ammeter increases. What happened to the reading of ammeter? Increases, and the resultant current decreases. What happened to the resultant current? Decreases when the coil is removed from the when the magnetic core or the coil is removed. Okay, and both the induced current and the current of the source becomes the same direction, so that is why the resultant current increases. When the coil is removed, the current increases temporarily. Okay, this happens temporarily because the source is DC here. Okay, to decrease the magnet temporarily due to the decreasing of the magnetic flux. Number 3, so guys, the self-induction will occur by changing the current. Okay, and also the current changes sometimes. The self-induction occurs by changing the current and by changing the magnetic field. How can we change magnetic field in self-induction? By inserting an iron rod into the coil, or by moving or removing an iron rod from the coil. If we insert the iron rod into the coil, what happens to the magnetic field? Increases. Flux increases. Induced current increases. According to Lenz's law, this increasing of the induced current, it goes to reducing and decreasing the net and the resultant current. So that is why the reading of the galvanometer drops or decreases. But when we remove the iron rod into the from the coil, what happened to the permeability? Decreases. The amount of magnetic field decreases. Flux decreases. Induced current decreases. This decreasing of induced current, according to Lenz's law, is opposite to the current of the source. So that is why they become the same direction, and the reading of the galvanometer and the reading of the amount of the current increases, the resultant current, and the reading of galvanometer increases. Number 3 and number 4, by variation of the current. If the intensity of the current is increased or decreased by changing the current, also the current induced in the circuit, the magnetic flux crossing the turn of the coil will vary. Okay. And number 4, a cell of back EMF is created when the current increases. When the current increases, a cell of back EMF is created in the coil. Okay. This cell of back EMF, it goes to decreasing and reducing the resultant current of the coil. Okay. Coefficient of self-induction L. What is this L? Negative L delta I over delta T. What is this L? This L is the coefficient of self-induction. L is equal to what? EMF over delta I over delta T. Guys, L is always positive. L is always positive. Why? Because I and EMF changes together. Okay? So that is why L is always positive, because L does not depend on EMF and the amount of the current period of time. Why? Because the amount of the changing, the variation of the current period of time changes with the EMF. Okay? Both of them increase and decrease together. So that is why L, the coefficient of self-induction, L, does not depend on EMF, does not depend on the change of the current period of time. And instead, it depends on what? It depends on the geometric shape of the coil, number of turns, and the length of the coil. So, the coefficient of self-induction is always positive and independent of EMF and the time rate of the changing of the current. What do you find out about the self-induction test? If the magnetic flux through the coil is varied due to the variation of the current in the coil, this variation affects the coil and leads to an EMF that resists the variation of the original current of the coil itself. This phenomenon is called self-induction. If the current I traverses a coil, the magnetic flux which crosses each turn of the coil is directly proportional to the intensity of the current. If the current varies at the rate delta I over T, the flux varies at the rate flux by T. So delta I over delta T is directly proportional flux over T. By increasing I, flux increases as well. Okay. When current is increased or when the coil is connected opposites of the source, okay, and they becomes the opposite direction, and EMF, the resultant EMF decreased and the resultant current decreased, becomes opposite direction. But when current is decreased or when the coil is removed, the resultant EMF increase, the induced the resultant current also increased. Here becomes minus, but here becomes positive. What is the function of the rheostat or variable resistor? By changing the rheostat. And how can we change the magnetic field? And how can we change the variation of the current? By the rheostat, we can change the amount of magnetic field. The self-induction of a solenoid. Self-induction of what? Solenoid. Of solenoid. Self-induction of solenoid. L is equal to what? Mu naught permeability, M square, the area of the coil, and length. What does coefficient of self-induction depend on? The coefficient of self-induction depend on the permeability, the square number of turns, area of the solenoid, and the length of the solenoid. The coefficient of permeability, the coefficient of self-induction is inversely proportional to the length of the coil, but it is directly proportional to the permeability, the square of number turn, and the area. What does the coefficient of self-induction depend on? The square number turn, cross-section area directly, length inversely, and magnetic permeability mu directly proportional. Now I'm going to prove this equation. Okay, this proof is not important. This is just for information. It's good to know. Okay, this is just for your knowledge. Now I'm going to prove this equation. How did we get this equation? According to Faraday's equation, guys. EMF is equal to what? Sorry. EMF is equal to negative N change flux over time. For the self-induction, negative L delta I over delta T. These two sides are equal, then the two other sides also must be equal. Negative N flux over time is equal to L flux, I over time. Time with time cancel. Negative with negative cancel. Delta with delta cancel. What does remain? N flux is equal to Li. Okay? N flux is equal to what? Li. L is equal to what? L is equal to N flux over I. Flux is equal to what? Flux is equal to AB. Cosine, it doesn't necessary. Okay? L replace. Instead of flux, write down AB. N AB over what? Over I. Now I'm going to prove the equation of coefficient of self-induction, which is equal to mu naught N square A over L. Guys, B is equal to what? For the solenoid, B is equal to what? B is equal to mu naught N I over L. And instead of this B, write down mu naught N I over L. N times A. And instead of this B, write down what? Mu naught N I over L. And what we have in the denominator? We have I. I with I cancel. What does remain? N times N, N. Mu remain. N times N, N square. A over L. The coefficient of self-induction depends on the permeability, the square number of turns, area of the solenoid, and the length of the solenoid. The coefficient of self-induction does not depend on the induced current and induced EMF. So that is why it is always has a positive sign. It can never be a negative. It's a scalar. Coefficient of self-induction, the ratio of the magnetic flux that crosses a circuit to the current that traverses it. Okay, L is equal to what? L is equal to the magnetic flux. The magnetic flux that crosses a circuit to the current that traverses it. To what? To the current that traverses it. Henry is the unit of coefficient of self-induction in a closed circuit. Okay. Henry is the unit of coefficient of self-induction. L is equal to what? Sorry, the equation of self-induction, EMF, L I over T. Okay, L delta I over delta T. L measured in Henry. What is the unit of L? Henry. Okay, measured in what? In Henry. If you rearrange this equation, L is equal to what? EMF I over T. L measured in what? Henry. What is the equivalent unit of Henry? Volt I ampere. Time it goes up, volt second over ampere. One of the equivalent unit of Henry, volt second over ampere. What? Volt second over ampere. If you remember, volt second is equal to what? Tesla meter square over ampere. And is equal to what? Weber over ampere. Okay? And instead of this Tesla, you can write down Henry is equal to what? Instead of this Tesla, you can open this Tesla, which is equal to Newton over ampere meter. In this equation, magnetic force QVB or BIL. B is equal to what? F over IL, Newton per ampere meter. And instead of this Tesla, write down what? Newton per ampere meter, meter square over area. Area becomes area square, meter with meter cancel. What is remain? Newton meter over ampere square. Newton meter over ampere. Newton meter is equal to what? Joule over ampere square. And Henry also is equal to volt over ampere hertz. And instead of this 1 over second, you can write down hertz, and volt over ampere is equal to ohm. Ohm over hertz. Henry is equal to ohm second. Ohm is equal to Henry hertz. So that is, you have to prove all the equivalent units of the Henry. Okay, it's very important, and you cannot memorize. You have to prove one by the equations. A sample problem 6a. The sample problem says an air solenoid of length 10 centimeter. The length of the solenoid is 10 centimeter. L 10 centimeter, 0.1 meter. You have to convert to meter. Cross-section area 25 centimeter square. A 25 centimeter square. Guys, be careful. To convert centimeter square to meter square, the SI unit of area is meter square, not centimeter square. How can you convert centimeter square to meter square? Multiply 10 power negative 4. So you have to convert this 25 centimeter square to meter square. 25 times 10 power negative 4 meter square. And 400 turn, number of turn is equal to what? 400 turns. It's traversed by a current. I initial is equal to what? 4 ampere. Calculate the magnetic flux. What is unknown? Flux, which crosses the solenoid. If the current reverses when the current is reversed, the amount of the current becomes negative with the same magnitude, negative 4 ampere. Why? Because when the current is reversed, positive 4 and negative 4 ampere, okay? In which time? 0.1 second. Calculate the induced EMF. EMF is unknown. How many unknowns do we have? 2. Guys, look. How can you solve this question? So first of all, you have to recognize the question. In this question, what is changed? Magnetic field, area, or current? Absolutely, the current is changed from 4 ampere to negative 4 ampere. Okay, the sign of the current changes. By changing the sign or the magnitude of the current, the self-induction is produced in the circuit. But before solving EMF, we have to find out the magnetic flux. Okay, we don't have magnetic field. We don't have like change in magnetic field. Here, the current is changed. According to the equation of self-induction, Li is equal to what? N flux. Okay, we proved this equation. Li is equal to what? N flux. Flux is equal to what? Li over N. Do we have I? Yes, 4 ampere. Do we have N, number of turns? Yes, we have it. 400 turns. Do we have L? Guys, this is not the length of the solenoid. Be careful. This is not L, the length of the solenoid. This is coefficient of self-induction. What is this? Coefficient of self-induction. This capital L, the coefficient of self-induction. Without coefficient of self-induction, we cannot determine the magnetic flux. How can we determine coefficient of self-induction? Mu naught N square A over L. Do we have mu naught? No, but it is R constant, 4 pi times 10 power negative 7. Number of turn 400 square. Don't forget this square, please. A, the area of the coil, 25 times 10 power negative 4 divided by 0.1. L is equal to what? After we found L, by calculator, L is equal to 5.03 times 10 power negative 3 Henry. Henry, you can replace into this equation to determine what? Flux. Now, do we have L? We didn't have, but we found 503, 10 power negative 3 times 4 current divided by 400 is equal to 5 times 10 power negative 5 Weber or Tesla meter square. In this way, you can determine the magnitude of the flux, okay, according to self-induction. Branch B, what is unknown? Induced EMF when the current is reversed. When the current is reversed from positive 4 ampere to the negative 4 ampere, I initial positive 4 ampere, I final is negative 4 ampere. The sign of the current is changed, so the EMF is induced in the circuit by changing the magnitude or by changing the direction of the current, because the current is a vector, it has both magnitude and direction. EMF is equal to what? Negative L for the same circuit, I, delta I over delta T. I final minus I initial over T. EMF negative. Do we have L? We didn't have, but we found. We can use the same 5.03 times 10 power negative 3 times I final negative 4 minus I initial positive 4 divided by time 0.1 second. EMF is equal to 0.4 volt. 0.4 volt. This is the induced EMF that created by the changing the direction of the current. Practice 6A, question 1. The electric current grows in a circuit from 0 ampere I initial. This is practice 6A, question 1. I initial is equal to okay, guys, look at question 1 in practice 6A. The last practice in this section. The electric current grows in a circuit from 0 ampere, I initial 0 ampere, and I final 10 ampere. The current increased, so delta I is positive, but EMF must be negative, okay? In how many seconds? Delta T, 0.1 second, okay? If the coefficient of self-induction of the circuit L is given 0.02 Henry, calculate the induced EMF in the circuit, because in this circuit the current is changed That is why we have to use the equation of self-induction. What is changed here? Current. By changing the current, the induced current is created in the circuit. So we have to use the equation of self-induction. Okay. EMF is equal to what? Negative L delta I over delta T. Negative L I final minus I initial over delta T. Negative 0.02 times final 10 minus 0 divided by 0.1. EMF, it should be negative 2 volt. Look, negative 2 volt. Which one leads to higher increase in the coefficient of self-induction of solenoid? Coefficient of self-induction in a solenoid. The coefficient of which one leads to higher, to increase the coefficient of self-induction in the coil, in a solenoid? Mu naught N square A over L. Doubling the number of turn or doubling its cross-section area. You have to look the equation, and the correct answer here absolutely is doubling of number of turn. Why? Because L is directly proportional to the square number of turn. L, it's still directly proportional to the area. By increasing area, coefficient of self-induction increases as well. By increasing number of turn, also the coefficient of self-induction increases. With both of them, coefficient of self-induction directly proportional. But why by increasing number of turn, the coefficient of self-induction becomes more and more? Because number of turn is square here. Okay, that is why number of turn, increasing number of turn has more effective than increasing the area of the coil, because number of turn in the equation of self-induction, coefficient of self-induction is square. So the answer, doubling number of turn. If the number of turn of the coil is doubled, if N2 is equal to 2 of N1 doubled, okay, when the line of the turn above the original one end of the same direction, what happens to the coefficient of self-induction? Coefficient of self-induction, L2 becomes quadrupled, 4 times of L1. Why? Because L is directly proportional to the square number of turn. If you decrease number of turn by factor of half, what happens to the coefficient of self-induction? Decreases by factor 1/4 or becomes quarter. But here, the new coefficient of self-induction becomes quadruple or increases by 4 times. Guys, that's all for today. Inshallah, in the next lesson, we will continue by explaining the eddy current, the last topic in this section in chapter 6, and I will solve the question of the section review in section 1 in chapter 6. Thank you for listening. Hope you benefited from my lesson.